Hello, dear friend. This is Lu from China Explorer Testing Company. Today, let's talk about XPS basic principles. XPS, which stands for X-ray photoelectron spectroscopy, is also known as ESCA, which stands for electron spectroscopy for chemical analysis. It's a widely used surface analysis tools for material that can characterize the elemental composition, chemical states, and perform semi-quantitative analysis. It has extensive applications in various material fields. Currently, the most commonly used XPS systems are many from these manufacturers: Alvec, Petri, Thermo Fisher, Kratos, and Specs. Petri, Thermo Fisher, and Kratos offer commercial XPS systems, while Specs provides customized systems. Different manufacturers offer different models and configurations to meet various applications. The basic principle of XPS is based on Einstein's photoelectric effect. Before discussing this theory, let's review the electron configuration outside the atomic nucleus. Typically, electrons in atoms are bound to orbitals of different energy level, donated 1, 2, 3, 4, corresponding to the main orbitals K, L, M, N. The closer an electron is to the nucleus, the lower its energy level, and the further it is from the nucleus, the higher its energy level. One X-ray with a certain energy are incident on the material surface. The atoms of the material absorb the energy of X-ray and excite electrons from core level. This entire excitation process is photoelectric effect, following the energy equation, where HV represents energy of X-ray. And in commercial XPS system, aluminum K-alpha X-ray with an energy of 1486.6 electrovolt are commonly used. This means that electrons with binding energy less than 1/400 have the potential to be excited. EB means binding energy, EK means kinetic energy, and phi is work function of instrument. Then the equation can be like this, simple one. In practical measurement, the kinetic energy of photoelectrons is connected, and the software converts kinetic energy into binding energy. For the element CD, for example, electrons in different orbitals can be excited as long as their binding energy is less than the incident beam. Electrons from orbitals closer to nucleus have higher binding energies, while those further away have lower binding energies. Therefore, an element can exhibit at least one or more peaks in XPS spectrum. XPS can identify elements from lithium to uranium. For typical XPS spectra, the X axis represents binding energy. It's displayed with low binding energy, higher kinetic energy on the right, and higher binding energy and low kinetic energy on the left. Elemental identification is achieved through binding energy information. The y-axis represents the intensity of photoelectrons. By integrating the peak areas, combining the relative sensitivity factor, you can perform semi-quantitative analysis of different components. Let's take example of manganese spectrum. With a nominal K-alpha X-ray excitation, you can observe manganese 2s, 2p, 3s, 3p photoelectron peaks, each corresponding to different intensities, you can see, and different binding energy. There are also older peaks, which will be discussed in future. As you know, XPS surface vector is used for qualitative analysis of elements, but XPS can also perform narrow scans to identify the chemical states. Narrow scans typically focus on characteristic photoelectron peaks, such as manganese 2p, which has strong peak intensity and typical peak shapes. We can use the binding energy information and typical peak shape to identify its different chemical states. So, where can we get binding energy information and standard XPS spectra? Usually from XPS handbook, database from software like Multipack and Advantage, as well as professional websites. These are all valuable resources for reference. That's all for today. It's the basic principles of XPS. Thank you for your time.